Now, believe it or not, the math does make sense, but to be independent, they shouldn't affect each other, right? If I'm independent from you and you go do something, I don't care. I don't care what the hell. So that's exactly what this says. If A given B, so B happens and A doesn't change, they're independent. So, and notice what I did on number 3. I did the same thing I did earlier. I made you do the work, and then I asked you a question. You just got to pick which work you've already done. So on number 4, you just have to compare 3A, which is the probability of male, right, with which one?
Female.
No. 3D, which is probably a male given owns a Toyota, right? If those are the same, that means me telling you they have a Toyota didn't change the probability they were a man, so they're independent. But did they stay the same?
No.
Probably a man was
45.
0.46 or so.
5.
40.
Yeah, 467.
458, whatever. Yeah. And then probably a male given Toyota was like 0.41.
407.
So what's really interesting in these studies, now there are several things here. I didn't tell you how I got these numbers, and I'll tell you now, I just made them, right? And on a quiz or a test, I always make the data you're looking at, or I try to, data from somewhere. True data I've gotten very often is the data you gave me about yourselves. But what could we say? Here's the really interesting thing about doing this kind of study. Having a Toyota, telling you that somebody has a Toyota, in this case, did what to the probability they're a man? It decreased, right? So aren't there things in the world that you want to know that about? If I knew this person was this, what's the probability they're this? And that's actually very fundamentally human, right? If you tell me you're from this place, I make a lot of assumptions because my brain goes, oh, the probability of all these things suddenly go up, right? You with me? So if you tell me you're from, oh crap, I gotta be careful. If you tell me you're from, what? If you told somebody else you're from California, they'll think, oh, probably their surfer kid went up. You with me? It kind of feeds into stereotypes, but the interesting thing about stereotypes is it's just our brain saying the probability went up. But very often we'll think, oh, that means they are that, right? And that's the bad step. It's just the probability went up. Doesn't mean they are that. It probably didn't go up to 100%. Are you guys semi with me? This is where things get really cool. The math, we get so stuck in the math, and the math is important. We have to be able to get the numbers before we can step back and say, what is it telling me? But we always look like the probability somebody passes a course versus the probability somebody passes a course given that they went to the Math Study Center. You with me? And hopefully we always want those numbers to show that the Math Study Center kind of helps. Now that goes into correlation and causation, right? We've got to be a little careful. But if the numbers ever went the other way, we would certainly be, oh shit. Well, what could that mean, though, in that case? If suddenly the probability, if you went to the Math Study Center, the probability that that person passed went down, it might mean the right people are finally going to the Math Study Center. Because who do you think currently goes there most of the time? The A students. Because they know what they need. Very often the ones that really need it, they don't know what they need. That's why they're doing so bad. But they don't go. So part of me was actually like, I always wanted those to go the other way. Because I go, well, the right people are probably coming. I doubt my tutors are hitting people over the head until they forget everything. Can you help me? Can you? Go away. All right, I didn't think that was happening, causing blunt trauma to their head. Right. You guys are semi with fingers. Talking about hitting students over the head, probably bad. Anything else on here that's surprising or you're not sure how it came out? Yeah.
3B, I'm not sure how that works.
Oh. So I did it the kind of the formula way. You could do it a little more directly. So 3B says Ford or female. So if I take the Ford owners, where'd they go? 51. And I add in the females, 65. How many have I double counted?
27.
27.
Okay.
Now some of you guys, hopefully some of you guys did it a better way. If you did 51 Ford owners, and then you went, I'm not going to add the 27, I'm going to add the 35 and the 3. I don't want to add the 27 twice. So you could have done 51 plus 35 plus 3. Either way you do it, it comes out to hopefully 89. So again, and this you don't hear very often from a math teacher, and I understand why, but very often in probability, the formula gets in your way. It'll always work. We just often put the wrong things in the wrong places. So when I have something I can count, probabilities are easy. I don't need a formula, and that's why they make it harder. I can just count. I don't need it. Like on number 1, I didn't give us anything to count. I had to use formulas to figure it out. Yeah. Anything else from there that's weird? I know a few people had problems with 3C. Right? Female and owns Hyundai. Is that a given? No. So the bottom is going to still be 120. And then on the top is everybody who matches what I'm looking for. I want somebody who's a female and they own a Hyundai. So there's only 3 people that match that. There's only 3 people that are both. So this should sort of match up a bit with a lot of the problems in the homework. A lot of problems in the homework look like number 1. So if you haven't done the homework yet, they will. And if you have, you know what I'm talking about. A lot of them are like that alarm clock problem, right? Some of them definitely look like number 2. Some of them look exactly like number 3 because they give you little charts that you have to read off of. So again, if you've done the homework, you know what I'm talking about. So I try to make the quiz a representative example of the major types of problems you see in the homework. And the thing there is, if you do the homework, you should have a decently easy time with the quiz. Because the quiz will basically be pretty much just like this, just with different situations.
Number 4.
Yes.
You pick it up the examples, but how if you do it exactly the way you asked us? If we say that the probability of male and the probability of owning a Toyota equals 55 over 120 times 59 over 120. Yeah, that should be not independent, right? Or dependent.
So another test for independence is if probability of A times probability of B is probability of A and B. But I just don't like necessarily going that way. But I think the book does talk about this a little bit. That's another test for independence.
Yeah.
So you can kind of show me that that's not true. But I personally like this one better because it's a lot more straightforward, actually. If B happens and A doesn't care. So I love that. This actually has in it the idea of why we call it independent. If B happens and A doesn't care, then they're obviously independent. It's one time in math you used a physical real world word in a way that is the same. It's nice.
So if they are different, you mean that they are dependent?
Definitely. If B happens and A's probability changes from what it used to be, then they're dependent. So if this is true, independent. Can you spell, Jeff? No. If this is not true, so you get this not equal to, then it's dependent. Because what's probably A? It depends on whether or not this happens, right? If it does happen, it's different from if it didn't happen. You with me? Or if I don't know it happened.
Yeah. Can you please calculate the way the top one? Can you do that for me? The formula, the top.
You can do it.
Yeah, I see.
Right? Probably a man times probably a Toyota.
55 out of.
But I'm not gonna. I'll do it after class because that's really a different way than what I wanted done. But I can show you. You can still do it that way, but I'll show you after class. Okay. Any other questions from that practice quiz? And again, the bottom line is, if you do the homework, that's it. That's the be-all, end-all of the math class, really. And it's not just doing it; it's getting help when you need it. So coming to see me, going to see a tutor. How many guys have been in to see the tutors? Have you had a decent experience so far?
There's only one tutor that knows stats over there.
Only one. Yeah.
So make sure if there's a tutor on the schedule that they have as a stats tutor, and you feel like they don't really know what they're talking about, you have to tell them, right? Because statistics, when I was the coordinator of the Math Study Center, I forced them to go through this My Math Lab assessment. And if they ever got below a certain grade on a test, they would stop being a stats tutor until they worked themselves back up. Because, you know, on one level, you got to realize to take one stats course and then to suddenly be a tutor for it. You with me? Yeah. That's not easy. So I'm not trying to make an excuse for the tutors. Just trying to let you know why that sometimes happens. They've gone through it, but they haven't looked at it nearly as deeply as the other math stuff. They've taken like 8 math courses beyond what you need help with. They're going to know their shit. Statistics, they've taken 1. Because how many courses here do we offer statistics? 1. We don't have a stats 2. You guys kind of with me? Now at the same time, there's a lot of good stats tutors over there. But it's been a while since I was a coordinator. They've hired more people. You've got to let them know if somebody's not up to snuff. You've got to fill out an eval and say, I don't think this person they didn't seem to really know what they're doing. Because I don't want people to go there and not go back. That sucks. You guys with me? And tell them too if they do a good job, right? Okay. So today, we're getting a little bit in chapter 5. Unless there's any questions, any other specific questions from homework for chapter 4? 4 or 5? Number 15? Oh yeah. Okay, cool. So the probability of a crash, we'll call it probability C, of any car in the US, they determined is 0.048. And this probability of crash happening during some given year. So the probability you're going to be involved in a car crash in a given year is just a little under 5%. You guys with me? Take the poker face off, man. You guys sort of with me so far. I mean, that's all I just repeated what they said. So 5% probability that you're going to be in a car crash in a given year. That sounds about right. Of course, that's over the whole U.S. So if you looked at any specific areas, it would definitely change. So an area in the middle of Wyoming would most likely be different than an area in the Bronx, for example. With it, much higher density there. But for anybody anywhere in the U.S., it's about 5%. So what's the probability that if a family has 4 cars, and in my brain, I'm already thinking how many spots I want for my hangman game. You guys have all played hangman? If you haven't, it's not some evil game. Nobody could possibly get hurt from it. But I think most of us have played hangman. So I'm already thinking I want 4 spots for my hangman game. I've got 4 cars, right? So they asked me what's the probability that at least one of them has a car crash. So again, this would so suck to do this directly. Because the first one could crash, or the second one, or the third one, or the fourth one, or the first 2, or the last 2, or the middle 2, or the first 3, or the last 3, or the first 2 and the last 1. Shit. I really want you to understand, you'd actually have to calculate each one of those situations' probabilities and add them up if you wanted to do this directly, which is a much better way to do this. The probability at least one crashes is 1 minus probability that none of them crash. So then I get 1 minus, here's my hangman game. What's probably the first card does not crash? 0.952. Yeah, 0.952. You with me? You guys see that? Yeah. And then the second one does not crash? 0.952. So again, that whole thing about the shortcut is I want 4 not crashes. There you go, see? I want 4 not crashes. So if the family had 8 cars, so there's probably at least 1 crashes, it would be 1 minus 0.952 to the 8th. I want 8 not crashes. Then when you do that in the calculator, you'll get the answer. So any given car, there's a 5% chance. Is somebody doing this right now in the calculator?
Yeah.
Is somebody? Yeah.
Yeah. It's 0.814.
0.814. So look what happens. There's a 5% chance that any given car crashes. If you have 4 cars in your family, there's an 81% chance that at least one of them will crash. Or wait, is that before you did 1 minus?
Oh yeah, that was.
0.178.
That makes more sense. It sounded horrible to me. 0.814 for this, and then 1 minus that, 0.186. So an 18, that sounds better. I knew it was going to be bigger, but not like 80%. So 5% chance that any car crashes. If you have 4 cars in your family, there's an almost 19% chance that at least one of them will crash. Of course, it probably goes up because now there's more chances, right? Okay. Thankfully, the probability that none of them crash is 81%. It's still pretty high. Thank God. Okay, cool. See, like I promised you, there are problems in the homework just like what I have on this practice quiz. So you see a lot of them that look like this. Okay. Any other questions from the homework?
Is that the end of it?
I think so. Is there any reason why the probability might be wrong? Basically, it's...
Yeah, is it because you're counting the cars? Wouldn't it be the individual? Like,
Yeah, what about the individual?
Wouldn't that 5% be if the individual gets in a car accident, not because of how many cars they have?
That's a good point. That's a point I didn't even consider.
Oh, they may not.
But I think the way they worded it, the probability of a selected car crashing, so it's not the individual. They actually did look at it from a car standpoint. What could be wrong is what I said earlier. Are they 4 teenagers? Are they 4 65-year-olds? Are they 4 varied ages? Do they live in Wyoming? Do they live in New York? You guys with me? Obviously, certain ages, and how do I know certain ages have different probabilities of crashing? All you gotta do is look at the insurance bill for people of various ages. Right? When you hit the magic age of 25, I remember this day.
But that could be the case of the tail light.
The insurance you get suddenly going way down because you magically know how to drive them. Of course, on average, people in that age range get in fewer crashes, so they pay less premium. Yeah.
That could be the case of the tail wagging the dog, though.
You gotta make it happen?
Well, your argument is that is happening because of it, but it could be in reverse. They were just saying that they're doing that because they feel that that's happening. That's why the rates.
Well, I'll tell you this,
going
for
up.
sure. The insurance company bases their rates on what they see.
Yeah.
So I know which way it's going. But I know kind of like what you're saying too.
Yeah.
But it is because of what they see happening. You're right, but there's maybe a little interplay.
Yeah.
But insurance companies base their rates on the probabilities of certain things happening.
Well, I was happy when I turned 25.
I know. Remember that day?
Oh, yeah.
Yeah. Suddenly, bam, it went way the hell down. I was like, what? Okay. Any other questions from chapter 4? Okay. So, a little bit of an intro to chapter 5. And I'm always, you know me, at this point, I think you know me a little bit. I'm always so desperately hopeful that you understand the difference between I'm trying to show you why a method works versus what you actually have to do as a student in this class. You with me? So I'm going to show you why what we do in this section works, and then I'll try to show you what you actually have to do. Because why it works is very long. You with me? But there's a shortcut. Once we see the pattern, math will say, there's a shortcut. Don't do all that crap. So let me do this. What do I have here? 1, 2, 3, 4, 6, 7, 8, 9, 10. Yay. Okay, so far it's really exciting. So take a second. What's the average of these numbers I put up on the board? Let everybody jump at once. I like this stuff. I think most of you guys can think about it in your head. Ready? I think it's 2.5, right? I might have done that too quickly.
12.5.
So 14, 16, 18, 20,
12.5.
25. 25 divided by 10, right? They add it to be 25.
12.5.
So the mean is the sum of x over n, so it's 25 over 10, 2.5. Right?
Yep.
Now, let me overanalyze the hell out of this. You will never have to do what I'm about to do. But I just wanted to make sense why it works. I could now, so what you guys did was this. Oh god, so let me do it a better way. You have 2 1s, cool, plus 4 2s, plus 1 3, plus 3 4s, cool? Okay, that's the way I would do it if I forced you to write it out. You'd say, so all right, Jeff, I'll write out some of it. Divided by 10. Now if you actually do that, you'll get here. Let me show you. There's another way to look at this. Isn't this 2/10 times 1? Plus 4/10 times 2, plus 1/10 times 3, plus 3/10 times 4. You with me? Can't I split up, what am I dividing by 10? This, and this, and this, and this. So can't I split them all up over 10? Still with me? Again, why would you ever do that? Don't. The only time you would do this is to explain why the shortcut works. Thank God there is a shortcut to this section. So isn't this 0.2 times 1? So isn't this 20% of 1 plus blah, 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 blah? Okay. So the reason we have this is if I have a large list of data with a lot of repeats. So for example, if I had in a room people and their ages, and there was a bunch of people about to graduate from high school and go to college. So say there's some 15, 16, 17, 18, 19. You with me? Don't judge the 19-year-old, he has some trouble. And there's a lot of them, so I'm just going to tell you the percentage of them that are 15 and 16. Right? I'm not going to be, we're not little kids. I'm 15, 3/4 years old. So you're 15 or you're 16. So I can put people in categories. There's 12, 15-year-olds, 16, 16-year-olds, just because. Let's do percentages, Jeff. That's better. So let's say there's 11% are 15-year-old, 15% are 16, 30% are 17. What do I have so far? 10, 20, 56. All right. Say 35 for 18. And so that leaves 9% for 19, I think. What am I being careful about there? Obviously, they have to add up to be 1. The whole 1, right? And do that, did I do that right? 5, 6, 9, well yes, thank God. So this sum is 1. And each probability is between what and what? What can each probability? It has to be between 0 and 1. These two things, those two things tell me this is a valid probability distribution. You with me? What have we made in the past back in chapter 2? Didn't you make frequency distributions and relative frequency distributions? So isn't this a probability distribution? It's just a choice of words. Isn't this a relative frequency, really? You guys with me? The thing that this is hiding, how many people do I have in this sample? Is there any way to know? If I had 100 people, how many would be 15 years old? 11. So you'd write 11 15s, 15 16s. So you could do it like this, but screw that. Thank God there's a better way to do this. How do you find the average? You multiply each probability by the number. Right? How do you find the average? We know how to find the average now from this extended look at this easy problem. You take 0.11 times 15, so you actually do this. X times P of X. The probability times the value plus the probability times the value plus. Multiply them, add them all up. That's if I have just a straight list of data. This whole thing I did here was to show you if you have a lot of repeats, is there a shortcut? Yes. So we did this the old way, and then we did it a slightly modified way. If you look at this, you'll go, who's the idiot who did this shit? Why would you do that? You with me? I mean, I don't blame you if you do, but it helped us out over there. Because now I know probability times value plus. So if I do each one, what's 0.11 times 15? Help me, 0.165? Or 1, yeah. Is it 1? Oh, sorry, yeah, 1.65, is that right?
Yeah, 1.65.
No, I don't know if I can keep that up. So help me out. 1.6. Yeah, it sounds right. 2.4. This one should be easy, Jeff. Should be. 5.1, is that right? And then that one, is whatever it is. What is it?
6.3.
6.3. And then that one, 1.71. Good, sounds right. So if you add those up, if you add up x p of x, if you add up the probabilities times the x values, that's the formula for the mean, the average. I like it. And what do you get when you add those up? I don't know. 16.1. Yeah, shit. 17.6. 17.16. Okay. So the average age from these people are 17.16. Why do you think it's a little over? Isn't the average of these numbers 17? Why is it a little over 17 for the average of everybody, really? Because where is most of the people at? Aren't they in here? So the average is going to be pulled up a little bit. Because you have more people that are older than 17 than you have younger. So of course the average is going to be a little bit over what it would be if it's just these 5 people. You guys semi with me here? Alright, so next time we'll talk about the other thing we need. We can find the mean. What else do we need to be able to find?
The median. The range.
Standard deviation. Cool. So we'll talk about how to find that.
You make those numbers up,
Say again?
you make those numbers up?
Here?
Yeah.
Totally. So you have to be given these 2 things. You're right. They have to give you these.